Hi guys, so let's begin our discussion over the questions of linear programming. The first question says that the solution set of the inequation 2x plus y greater than 5 is what? So when I talk about this inequation, it is strictly greater than 5, right? So how do you interpret this? Now 2x plus y equals to 5 is what first of all we need to talk about. 2x plus y equals 5 is going to be which line? Well, when you put x equals 0, you get y equals 5. And when you put y equals 0, you get x equals 5 by 2, which is 2.5. When you join these 2 points together, you get this straight line, which is actually 2x plus y equals 5. Now when I am talking about the region greater than 5, all the points on this line are actually satisfying 2x plus y equals to 5. What are the x comma y's which satisfy 2x plus y strictly greater than 5? For that, what do? We check the origin. If you put x equals 0 and y equals 0, you basically get 0 plus 0, that is 0, which is not greater than 5 but less than 5. So the region which is containing the origin is actually the region of all the x comma y's for which 2x plus y is less than 5. I want 2x plus y greater than 5, which is towards the other side, the other region, which is not containing the origin. So this is that region which consists of all the points x comma y for which 2x plus y is strictly greater than 5. I am not including this line because on this line lie those ordered pairs for which 2x plus y is equal to 5. I want strictly greater than 5. So exclude this line, and the region, the other side, is the required region. This is 2x plus y strictly greater than 5. So the region is actually open half plane not containing the origin. Clear? Let's move on to the next question. We have objective function of an LPP. So this is just regarding the concept. Objective function of an LPP is not a constraint. It is, yes, a relation between the variables, but more than that, it is a function to be optimized. We need to optimize that, either maximize or minimize, depending upon whether it is profit function or cost function, right? So depending upon it, it is a function which needs to be at the end of the day optimized. Next question we have, which of the following sets are convex? Now see, this is pretty important to realize what a convex set is. So if I talk about the first set, it is all the ordered pairs for which x square plus y square is greater than equal to 1. If I talk about equal to 1, x square plus y square equal to 1 is actually a unit circle centered at origin. This is x square plus y square equal to 1. I want x square plus y square greater than or equal to 1. Now if you put x equals 0, y equals 0, you get 0 plus 0, which is not greater than 1. That means the region not containing the origin is the region x square plus y square greater than equal to 1. Here I am including the boundary also because I want equal to 1 and greater than 1. So x comma y's for which x square plus y square is equal to 1 are these points on the boundary, and for which this is greater than 1 are all the other shaded points, right? So this is my region x square plus y square is greater than equal to 1. Is this convex? Convex means in this shaded region, when I take any 2 points and I join them, is the line segment joining the 2 points also completely lying in the shaded region? No, it is not completely lying in the shaded region. There is a part of it which is coming in the non-shaded region. The moment I have found 2 such points, which when I join the line segment is not completely in the shaded region, that means this is not a convex set. So no, this is not convex. If I talk about the other one, y square is greater than equal to x. So when I talk about y square equal to x, it is actually rightward opening parabola. This is y square equals x. If I talk about y square greater than or equal to x, so equal to x we have plotted the boundary, greater than x will be in the interior or exterior? Greater than x, that means if you just pick up any point which is not lying on the parabola, if you pick up say -1, 0, If you pick up minus 1 comma 0, x equals minus 1 and y equals 0 is going to show you 0 is greater than minus 1, which is true. That means the boundary as well as this shaded region is actually y square is greater than equal to x. Right? This is y square is greater than equal to x. Now, if this is the region which is given by the very question, is this convex? Again, I have 2 points in the shaded region which when I join, the segment is not completely lying in the shaded region, and therefore this is again not a convex set. If you talk about the third case, again it is representing an ellipse and greater than equal to something, that means it is the exterior of the ellipse. So again the situation will be ellipse will be here and the exterior of the ellipse is actually my region. So if you take any 2 points in the exterior of the ellipse, you join them, the line segment is going to cut through the ellipse. That means the entire line segment is not going to lie in the exterior of the ellipse. Therefore again this is also not a convex set. If I talk about this set which is y is greater than equal to 2 and y is less than equal to 4. So y is greater than equal to 2 and y is less than equal to 4. Say this is y equals 4 and this is y equals 2. I am saying y is less than equal to 4 and y is greater than equal to 2. Basically I am talking about this region, including these 2 lines and everything in between it. So here if you take any 2 points in the shaded region, any 2, the line segment joining them is always going to lie in this shaded region, and therefore the region represented by D is yes a convex set. Talking about the next question we have, which among the following is feasible solution of the LPP? Now for this you should be very clear with the definition of feasible solution. Feasible solution is first of all a solution. Next thing is that it is feasible. That means first of all the coordinates should satisfy all the constraints, or I can say the coordinates should satisfy this and this. But if the coordinates are satisfying the non-negativity constraint as well, the solution becomes a feasible solution. Here you can see if I talk about C and D are going to satisfy the first and the second constraint, but they are not satisfying the non-negativity constraint. So they are solutions, but they are not feasible solutions. Whereas if I talk about the option number A, that is x equals 2 and y equals 3, if you plug in x equals 2 and y equals 3, you get 3 into 2 6 plus 2 into 3 6, 6 plus 6 12, 12 is yes less than 30, and if you put it in here you get x equals 2, y equals 3. So you get 2 plus 6, that is 8, 8 is definitely less than 22. So this basically this pair of variables, pair of values of the variables is satisfying the 2 constraints, and it is also satisfying the non-negativity constraint because both of them are non-negative, and therefore only this among all these 4 is a feasible solution. Mind it, C and D are solutions, but they are not feasible because you can see this is both negative, here this is negative, it is not satisfying the non-negativity constraint. Clear? Moving to the next question we have, the optimal value of the objective function is attained at, so this is something very easy. Where is it attained? It is actually attained by the corner points of the feasible region. Feasible region is always a convex set. It has corner points. We basically determine the coordinates of the corner points, and those corner points give us the optimal value. Clear? Moving to the next, we have the minimum value of z equals 20x plus 10y subject to all these constraints is what? So the question is asking us the minimum value of this particular objective function subjected to these constraints. Let's try to understand what is actually the feasible region. First is x plus 2y less than equal to 40. What do we do? X plus 2y equals 40. When x is 0, y is 20. When y is 0, x is 40. So you basically get a line like this. When x is 0, y is 20. When y is 0, x is 40. This is x plus 2y equals 40. Let's talk about the next one. We have 3x plus y is greater than equal to 30. When x is 0, y is 30. And when y is 0, x is 10. Okay? When x is 0, y is 30. And this is 10 comma 0, because when y is 0, x is 10. Then you have 4x plus 3y is greater than equal to 60. So when x is 0, y is 20. And when y is 0, x is 15. So you basically get something like this. This is 15 comma 0. And when you talk about the feasible region, this happens to be the feasible region. Very easily you can compute all the corner points of the feasible region. This you already know, this is 15 comma 0, this is 40 comma 0. What is this and what is this? This is nothing but the intersection point of this and this. That is, what is this line? This line was x plus 2y equals 40. This line is 4x plus 3y equals 60. And this line is 3x plus y equals 30. So basically this point is the intersection point of 3x plus y equals 30 and x plus 2y equals 40. This point is going to come out to be 4 comma 18. And if I talk about this point, which is the intersection point of 4x plus 3y equals 60 and 3x plus y equals 30, this is going to come out to be 6 comma 12. When I talk about all these 4 points, which are the corner points of my feasible region, which is the shaded region, I actually, to get the minimum value of z, compute the very value of z at all these 4 points. So the first one is 4 comma 18. At this point, z is equal to what? 20x plus 10y. 20 into 4 plus 10 into 18, which is 80 plus 180, which is 260. Then I have 6 comma 12. Z is 20x plus 10y, which is 120 plus 120, which is 240. Then you have third is 15 comma 0, which is 20 into 15 plus 10 into 0, which is 300. And last you have 40 comma 0, which is 20 into 40 plus 10 into 0, which is 0. So 20 into 40 is 800. The minimum value therefore comes out to be 240. So what is the minimum value? The minimum value is nothing but 240. Clear? Moving on to the next question, we have the objective function z equals 2x plus 3y subject to these constraints can be maximized at how many points? Let's see. That depends upon how the feasible region of this objective function basically is behaving. If I talk about the plotting of the constraints and hence determination of the feasible region, what do I get? Let's see. I have x plus y is greater than equal to 2. So this is going to give you a very simple line. X plus y equals 2. This point is 2 comma 0. This point is 0 comma 2. Then you have x plus 2y equals 3. When x is 0, y is 1.5. And when y is 0, x is 3. So this happens to be the case. This is x plus 2y equals 3. This point is 3 comma 0. This is 0 comma 1.5, because when x is 0, y is 1.5, when y is 0, x is 3. And when you try to get the region x plus y is greater than equal to 2 and x plus 2y is greater than equal to 3 and x and y are non-negative, you basically get this as your feasible region. You know that this is an unbounded region in the first quadrant. You know that as far as I go, more and more or larger and larger the value of objective function I can obtain. As far and far and far I go in the first quadrant, the coordinates of x comma y are going to become larger and larger, and hence the value of z is going to become larger and larger. So I can maximize my z to at most level as I want. So that means the objective function can be maximized at an infinite number of points, right? Because as I go ahead and ahead and ahead, the coordinates basically keep on increasing in values, x coordinate or y coordinate, and hence the value of z keeps on increasing and becoming larger and larger, and hence becoming maximum and maximum. So I can maximize it at infinitely many points. Next question says what? Let's see. Which of the following statements is correct? Every LPP admits an optimal solution. No, that's not true. There are LPPs which do not give you any optimal solution. This is drastically incorrect. An LPP admits a unique optimal solution. No, it can obtain more than one optimal solutions. If an LPP admits two optimal solutions, it has an infinite number of optimal solutions. Yes. It can happen that an LPP does not possess any optimal solution. It can happen it possesses a unique optimal solution. But if it is possessing more than one optimal solutions, it has to be possessing infinitely many optimal solutions, okay? So either one or none or infinitely many. So yes, this is true, and the set of all feasible solutions of an LPP is not a convex set. This is wrong because it is very much a convex set. We have studied it as a very good established result, right? Moving on to the next question, we have the region represented by the inequation system. So there is a system of inequations given to you. You are asked to determine the region represented by them. X plus y is less than equal to 30. Let's talk about this now. X plus y is less than equal to 30. Let me say, this is it. Let me say this is 30 comma 0 and this is 0 comma 30. This is x plus y equals 30. Then you have x is less than equal to 15. So x is less than equal to 15. I am talking about everything in here. So this point, this is x equals 15. After this I have y is less than equal to 20. So somewhere here is 20. Y is less than equal to 20. This is y equals 20. And x plus y is greater than equal to 15. So this is 15. Here it will be somewhere 15, so you basically get this, right? This is 15, okay, and this is also 15. So the feasible region that you obtain comes out to be this region. Because you wanted everything less than equal to 15, after that you wanted greater than equal to 15, after that you wanted less than equal to 20, right? So this happens to be your feasible region, which is very much a bounded set in the first quadrant. It is a very much bounded set in the first quadrant. Moving on to the next question, we have the point at which the minimum value of 10x plus 4y subject to these constraints is what point? Which is that point where this function obtains its minimum value. For that again we will have to plot the very coordinates. Plot the constraints. You have 4x plus y equals 80 when you see when x is 0, y is 80, and when y is 0, x is 20. So you get this is 0 comma 80 and this is 20 comma 0, right? So you have 4x plus y equals 80 is this constraint. Then you have 2x plus y equals 60 when you see when x is 0, y is 60, when y is 0, x is 30. So this is 0 comma 60 and this is 30 comma 0. So when you talk about the common region, you get this unbounded region in the first quadrant as the common region. Obviously, this is one of the points to consider. What is this point, intersection point of both these constraints, which is 4x plus y equals 80 and 2x plus y equals 60, right? After this you know that y can be written as 60 minus 2x. 60 minus 2x equals 80. Now 80 minus 60 gives you 20, so 2x equals 20, x equals 10. When you put x equals 10, you get 40 plus y equals 80, so y comes out to be 40. This point is 10, 40. When you talk about the values, you have to compute the minimum value. Fine, if it was a maximum value question, then that cannot be determined. There is no point actually which is going to give you the maximum value in here, because it's an unbounded region. As far as you go, the value of z keeps on increasing. But the question is about the minimum value, so we have these 3 points to check. This is 0, 80, 10, 40, 30, 0. If I talk about 0, 80, my z is 10x plus 4y, 10 into 0 plus 4 into 80, which is 320. Then you have 10, 40. Z is 10 into 10 plus 4 into 40, right? So this is 100 plus 160, which is 260, right? And then you have 30, 0, which implies Z is 30 into 10, which is 300 plus 4 into 0, so this is actually 300. So minimum that you are getting is 260 at the point 10, 40. So your answer is 10, 40, the point at which Z is attaining its minimum. That completes our discussion over the questions. That's it from my side. Thank you.